This is where calculus gets fun. Integration by substitution. This is easily the most complex procedure you'll learn in Calculus 1 or AP Calculus AB if you're in high school. But let me assure you, this really isn't that bad as long as you work to understand where it stems from. And that's the chain rule. So let's take it back a few lessons. Remember that if we were to perform the derivative with respect to x of a composition of functions, so f of g of x, we would receive f prime of g of x multiplied by g prime of x. Now let's not forget that the main idea behind antiderivatives is working backwards, and integration by substitution is working backwards from the chain rule. So if we had big f of x, remember big f of x, we used that to represent the antiderivative of f of x, little f. So if we were to take the derivative with respect to x of big f of x, that would give us f of x. Because remember, the derivative of big f of x was big F prime of x, which then gave us little f of x. So that's what I'm saying. We're just using big f of x to represent the antiderivative. And so, using that logic, if we were taking the derivative with respect to x of big F of g of x, this would yield f of g of x multiplied by g prime of x, just like that. And so what this means is that if we were to perform the indefinite integral of f of g of x multiplied by g prime of x with respect to x, this would give us big F of g of x plus c, because remember, plus c is included with all indefinite integrals. Now, there are integrals which are easy enough to complete with pattern recognition. Here's an example. Suppose we were asked to compute the integral of cosine of x squared times 2x, and we're computing this integral with respect to x. Notice that we have x squared on the inside of cosine and then a 2x on the outside. We should also notice that the derivative with respect to x of x squared is 2x. And so with that said, we should be able to realize that, hey, the chain rule happened when we worked forward. And because integration is going backwards, it's the inverse of the derivative, it seems that we performed the derivative of this portion of the function and then applied the chain rule because we left this the same and then applied the chain rule afterwards. And so that's what we need to start practicing, working backwards with the chain rule, because using this idea, we can note that the inside function, or g of x, is x squared. Now, the only thing is, we have f. Well, what's f? That's cosine of something. F of something, cosine of something. So we have cosine. Well, what's the antiderivative of cosine? That's going to be sine. And so we can confidently say that the antiderivative or indefinite integral of cosine of x squared times 2x dx will be big F, so that's the integral of cosine, which is sine of g of x. So g of x is x squared. And notice that g prime, which is 2x, it doesn't really matter. It doesn't appear here because when we go forwards, when we take the derivative, it will pop back out. That 2x will pop out. And so our integral of cosine of x squared times 2x dx is equal to sine of x squared plus c. And so pattern recognition is just one of the ways to tackle these types of integrations. If you receive more complex integrals or need to see it worked out on paper, please feel free to use substitution. And here's how it works. So again, the integral of f of g of x multiplied by g prime of x with respect to x is equal to big F, and remember big F is just the antiderivative of little f, so big F of g of x plus c. But let's say we didn't know this for a second. Let's go ahead and erase that. So if we're looking at this integral, let's go ahead and make a substitution. I'm going to go ahead and say that u, so some letters, this is a variable, u, I'm going to replace it with g of x, just like that. And so if I were to do that, I would be able to rewrite my integral. We would have the integral of f of u times g prime of x dx. But wait, we can't do anything here because we'd be integrating a u variable with respect to an x variable. That's a huge no-no. But we can definitely fix this. So again, over here on the side, I'm going to restate that we let u equal g of x. Now, if we were to go ahead and take the derivative with respect to x of both sides, we would receive the following. We would have d dx of u, so the derivative of u with respect to x equals the derivative with respect to x of g of x. And this would go ahead and give us g prime of x multiplied by dx dx, and that's just 1. So we would have du over dx equals g prime of x. Now watch what I'm going to do very carefully. I'm going to go ahead and rewrite this derivative in its equivalent differential form. And essentially what you do is we would grab that denominator, that dx, instead of saying with respect to x, this will now become the differential of x. And so we can go ahead and multiply dx on both sides. And that'll leave us with du equals g prime of x dx. Now, I want you to notice something very, very, very interesting. G prime of x dx is located in our integral. It is right there. So circling them both, we can see that du, since du is equivalent to g prime dx, we can go ahead and make that substitution. So that's why this is called integration by substitution. We're making these substitutions to help us see the integral in the way that we need to, which is working backwards with the chain rule. And so upon making that substitution, we can now say that we have the integral of f of u now multiplied by du, because we have now substituted g prime of x times dx with du. And there we go. Now we can go ahead and make this integration because we have f of u with respect to u. Think about it. If we had the integral of f of x with respect to x, that would just be big F of x plus c. The same goes. We can go ahead and just replace x with a u variable as long as we are integrating with respect to u. Because these are just letters, guys. These are just variables. As long as we're consistent with all of our variables, we can use whatever we want. We can use whatever we want. So, with that said, this over here, this integral, the integral of f of u du, will be big F of u plus c. And now at this time, we can go ahead and make a backwards substitution. We can go ahead and back substitute the u equals g of x. So this means that this integral is equivalent to f of g of x plus c. And this is big F. This is the antiderivative of little f. So let's solidify this by going over that example that we did before one more time. So earlier we computed the integral of cosine of x squared multiplied by 2x with respect to x. Now again, just like last time, we were looking for that pattern because we were looking for what substitution we should have made, and that was the g of x because that was going to give us g prime. In this example, and actually, a good tip that I can give for all integration by substitution problems is always make u the term beneath the highest level. So here's what I mean, or look for your outer level. In this problem, we are looking at our most complicated term. That's the cosine of x squared. 2x on its own, that's not very complicated. So let's go ahead and take a look solely at cosine of x squared. Now, there are multiple levels here because it's complex. That's why it's complicated. 2x is just one level. Cosine of x squared, that's two level because it's separated by parentheses. So my rule is I always make u the level underneath the most complicated term. Our most complicated term is cosine of x squared. The level underneath the cosine of x squared, well, that is just x squared. That is on the level beneath. So that's exactly what I'm going to do. I'm going to set u equal to x squared. Upon doing that, I'm going to go ahead and compute the derivative of both sides with respect to x. So du dx equals 2x. Upon converting this to its equivalent differential form, I'll receive du equals 2x dx. Hey, look at that. Notice 2x dx, 2x dx. Hey, we can make a great substitution here. So upon doing so, we'll now have the integral of cosine of, okay, look at that. That's our substitution. X squared equals u. So we have cosine of u. 2x dx. 2x dx over here, we can replace that with du. So multiply by du. And there we go. And so we can go ahead and state that we're taking the integral of cosine of u du. And that's the same thing as saying cosine of x dx, if you want to think about it that way. And so that will be equal to the sine of u plus c. And so from here, we can go ahead and completely finish this problem by back substituting what u equals, which is right there. So u equals x squared. So our final answer is sine of x squared plus c. And so that was my general guideline for integration by substitution. If you're still confused, don't worry. For basic integration by substitution problems, do the following. We always want to make u the level underneath the most complicated term. Try solving the following problems using my tip. The first problem is computing the integral, the indefinite integral, of the quantity of x squared plus 3, all raised to the 7th power, multiplied by 2x dx. Another problem is the integral of the quantity of 4x cubed plus 2x, all raised to the 6th power, multiplied by 12x squared plus 2, and we're taking this integral with respect to x. In identifying the most complicated terms, we see that in the first one, that's going to be the quantity of x squared plus 3 all raised to the 7th. We can clearly see that there are two levels there, only one level with 2x. Similarly with the right, we see that the most complicated term is the one with two levels, 4x cubed plus 2x all raised to the 6th power. That is our most complicated term. I'll let you figure out what's going to be the level underneath that. And you'll see that it works just fine. So take a look at some example videos to solidify your understanding, as this is where your brain will be challenged the most. So we'll see you next time.